Explanation for how to detect a cycle in a linked list. It's called Floyd's algorithm. It's called the tortoise and the hare. It's called the slow and fast pointers. Um, and so here is a linked list that has a cycle, as you can see. Um, Now you can see it holistically here visually for this example, but you don't have this luxury in real life because you don't have visibility into the rest of the list. You only get the pointer to the head node here. So, this list could be a million elements long. You don't know going in. So, there needs to be some kind of clever algorithm for detecting this. Okay? Um, so, another way, so the way we're going to visualize this is a little bit differently, but the same linked list. So we'll visualize it like this. Okay, and put a circle here like this. Okay. So this is the same linked list. So in this case, we'd have like a 0 here, a 1 here, 2 be here, maybe a 3 up here, 4 here, 5 here, 6 here. Okay, so the values of the linked list nodes here are, ordinal, very clean, but obviously it's the pointers that matter here. So, the numbering scheme here just kind of helps visualization, but just keep in mind that the actual values in the list nodes could be anything. It's really the pointers that we care about here. So the way that the fast and slow algorithm works is we have a fast pointer and a slow pointer. Okay, and let's say they both start off at 0 here, and it's very simple. You just iterate in a while loop, and you always move slow up by 1, and then you move fast up by 2. So 1, 2. Okay, so this is the end of the first iteration. Second iteration, slow up 1, fast up 2. Right. Next iteration, slow 1, fast 1, 2. Then we get slow 1, fast 1, and then we cycle 2. Slow 1, fast 1, 2. Okay. So this is the termination condition. This is when we know we have a cycle, if the fast and slow pointers ever point to the same node. Okay. Um, and this runs in O of n time. And it's guaranteed to find a cycle. And so to explain that, let's kind of consider like a worst case scenario here where the slow pointer is here, maybe the fast pointer is here. Okay. So let's consider the gap between these. The fast pointer is moving away from the slow pointer, attempting to lap it effectively. And so let's consider kind of the distance that is required for the lapping to happen. And you might think, like, is it like could it just skip right over the slow pointer when it laps? No, it's guaranteed to find it in O of n time, and here's the very simple logic behind that. So let's consider the gap, right? And what happens to the gap at each iteration of this algorithm, right? So the gap right now will be, in this case, like 1, 2, 3, 4. That's the length of the gap, the distance between the fast and the slow. Again, fast moving faster, so it's going to be catching up with the slow, but of course the slow is moving as well. So what's the change to the gap at each iteration? Okay, So let's consider the fast pointer is going to move 2 forward each time, right? Which closes the gap by 2. So it'll be the previous gap distance minus 2 from the slow pointer, from the, yeah, anyways. And then the slow pointer is going to be moving forward by 1. And the slow pointer moving forward actually increases the gap. So increases it by 1. So if we collapse this, we get that each iteration, the gap decreases by 1. Okay, so that means that at some point, because the gap is only changing by 1, that they will eventually converge. Okay, and then it is O of n time y, because well, the size of the gap is bounded by the size of the list, right? Like this gap will never be bigger than n, right? And because we're you know, we want to keep iterating until the gap is equal to 0, right? And so the max number of compute cycles or iterations here is bounded by n before the fast and slow pointers meet. So that is it.